Hello students, welcome to EPG Pathshala. I am Gaurav Gupta from Sharda University. Today we are going to talk on module Inventory Control Systems Periodic Review System under paper Operations Management. This chapter would help students to understand periodic review inventory control system. Second, concept of service level and determination of reorder point when demand is uncertain. Introduction. Previous chapter discussed one of the inventory control systems where stock level was tracked after every withdrawal of items. Though this method helps in mitigating the effect of uncertainty in demand patterns but becomes time consuming and sometimes irrelevant. For instance, checking inventory level, less important items and done very frequently, such as nuts and bolts, would be time consuming and unnecessary. Also, when there is certainty of supply from the vendors after a particular time period, then there is no need to check stock level after every usage. In such cases, periodic review system is applicable. This chapter focuses its discussion on this type of inventory control system. Periodic review P system. In contrast to the continuous review inventory system considered, we now assume that the system is only being monitored periodically. At the end of each period, when the current inventory level is determined, a decision is made on how much to order, if any, to replenish inventory for the next period. Each of these decisions takes into account the planning for multiple periods into the future. We begin with the simplest case where the planning is only being done for the next two periods and no setup cost is incurred when placing an order to replenish inventory. One option with the stochastic period review inventory system is to plan ahead only one period at a time. Using a stochastic single period model from the preceding section to make the ordering decision each time. However, this approach would only provide a relatively crude approximation. If the probability distribution of demand in each period can be forecasted multiple periods into the future, better decision can be made by coordinating the plans for all these periods than by planning ahead just one period at a time. This can be quite difficult for many periods but is considerably less difficult when considering only two periods at a time. Assumptions. Except for having two periods, the assumptions for this model are basically the same as for the one period model presented in the preceding section as summarized below. Each application involves a single stable product. Planning is being done for two periods where unsatisfied demand in period 1 is backlogged to be met in period 2, but there is no backlogging for unsatisfied demand in period 2. The demand D1 and D2 for period 1 and 2 are independent and identically distributed random variables. The initial inventory level before replenishing and beginning of period 1 is x1 greater than equal to 0. the decision to be made Y1 and Y2 the inventory levels to reach by replenishing if needed at the beginning of period 1 and period 2 respectively. The objective is to minimize the expected total cost for both periods where the cost components for each period are C equal to unit cost for purchasing or producing each unit, H equal to holding cost per unit remaining at end of each period, P equal to shortage cost per unit of unsatisfied demand at end of each period. For simplicity, we are assuming that the demand distributions for the two periods are the same and the value of the above cost components also are the same for the two periods. In many applications, there will be differences between the periods that should be incorporated into the analysis. For example, because of assumption 2, the value of P may well be different from the two periods. Such extension of the model can be incorporated into a dynamic programming analysis presented below, but we will not delve into these extensions. Two scenarios of P model. Under this system, inventory level or remaining number of units in the stock is checked after certain and fixed time period. This system is also termed as fixed interval reorder or periodic reorder system. As the title suggests, next order is placed after a certain fixed time period. For instance, a soft drink vendor makes weekly round to every retailer to check the inventory level. This helps the retailer as well because retailer would be sure of the time period when the vendor would visit for supplies. But this system has its limitations which have been discussed in following two sections. If demand is uncertain before reorder point, as P system checks inventory level only after fixed time period, so if the demand is strong during the time period before decided time of checking stock level, then next order of the batch would be higher to compensate for high demand. Similarly, if demand is slow during such time period, the number of items left in stock when it is checked would be higher and so retailer would place a smaller order. If demand is uncertain after reorder point, after placing next order at reorder point, stock is not checked till order is received. Variation in demand, whether high or low, would impact size of new batch. These two cases have been discussed in the following section with illustrations. Periodic review system with uncertain demand before reorder point. Suppose batch size that is Q equal to 100 units, daily demand D equal to 10 units and lead time L equal to 5 days. Lead time is the time taken by the supplier to replenish stock by Q after order has been placed. If daily demand would have been fixed and certain of 10 units, then 100 units would be consumed in 10 days, making time between order to be of 10 days as shown in figure. The time between order and quantity would remain same in case of certain daily demand. Case 2. Suppose from a batch size of 100 units, daily demand before reorder point varies in such a manner that demand during day 1 is of 20 units, during day 2 is 10 units, during day 3 is of 5 units, and during day 4 is of 15 units. For remaining days, daily demand is constant at 10 units daily. With lead time of 5 days and review being done only after a fixed time period of 5 days, the variation in demand would lead to situation of stock out. Under the given scenario as shown in figure, first 50 units are consumed in first 4 days, and as next 50 units would be consumed in next 50 days, making time between order as 9 days, so entire batch would be consumed in 9 days, leading to stock out on 10th day. Under such situation, next order should have been placed after 4th day. But because of P system, order would be placed only after 5th day of Q equal to 110 units. Case 3. Suppose a batch size of 100 units. Daily demand before reorder point varies in such a manner that demand during day 1 is of 5 units, day 2 it is of 10 units, during day 3 and day 4 it is of 5 units, and during day 5 it is of 15 units. For remaining 5 days, daily demand remains constant at 10 units. Under this scenario, in first 5 days, only 40 units are consumed, and as review is done after 5 days, an order of Q equal to 100 units is placed. For next 5 days, a total of 50 units are consumed, making a total of 90 units at the end of one ordering cycle as shown in figure 1c. When new order is made available, the stock still had 10 units, thus increasing the stock to 110 units. So for next order, manager would order only 90 units to keep the stock level at optimum. This indicates that total TBO remains same as 10 days, but quantity order changed as shown in figure. As the table shows, day 1 d equal to 10, remaining units nil. Case 2 d equal to 20, remaining units nil. Case 3 d equal to 5, remaining units nil. Case 1 day 2 d10, remaining units 90. Case 2 d10, remaining units 80. Case 3 remaining units 95. Case 1 day 3, remaining units 80. Case 2 D5, remaining units 70. Case 3 D5, remaining units 85. Likewise, in day 10 D10, remaining units 10. In case 2 D10, remaining units 0. In case 3 D10, remaining units 20. These three cases clearly indicates that in P system the TBO remains same of 10 days. Batch size varies because of varying demand. Q was 100 units in case 1, 110 units in case 2, and 90 units in case 3. Reorder point, that is time when order is placed, is same, that is next order is placed only after 5 days. In P system, as seen from above illustrations, estimation of reorder point does depend on varying demand before lead time, as stock level varies after every ordering cycle. Periodic review system with uncertain demand after reorder point. As shown in previous section, estimation of reorder point in P system does depend on variation in demand before lead point. But what happens if demand is varying after lead time? This has been discussed by illustrating following cases. Suppose a batch size of 100 units in the stock, and for first 5 days 10 units daily are consumed. Thus after 5 days a stock of 50 units is left. Now as lead time, that is time between placing and receiving an order, is of 5 days, so order is placed after 5 days assuming that by the time next batch of 100 unit is obtained, remaining stock of 50 units would be consumed. Also, stock is reviewed after 5 days, so making reorder point as when 50 units are left. Case 1. Suppose demand after 5th day varies in such a fashion that 5 units are consumed on 6th day, 10 on 7th day, 5 on 8th day, 15 on 9th day and 5 on 10th day as shown in figure. Thus, a total of only 40 units out of available 50 units are consumed. This results in formation of safety stock of 10 units. Also, after a periodic review at 5th day, if an order of 100 unit is ordered, then total inventory position would be of 110 units, increasing holding cost. So, estimation of reorder point depends upon variation in demand after during lead time period. These extra 10 units are called as safety stock. Thus, stock at ROP level R equal to 50 minus demand during lead time L equal to 40 equal to safety stock SS equal to 10. Case 2. Suppose demand during 6th and 7th day is of 20 units and during 8th day is 10 units. So all remaining 50 units are consumed in 3 days as shown in figure, whereas order would be replenished only on 10th day, making a situation of stock out during 9th and 10th day. During 6th day, D5 remaining units 45, case 2 D20 remaining units 30. In case 1 during 7th day D10 remaining units 35, case 2 D20 remaining units 10. So, in case 1 during 8th day D5 remaining units 30 and in case 2 D10 remaining units is 0. Similarly, in case 1 on 10th day D5 and remaining units is 10. These two cases clearly indicate that if demand is weak during lead time, it will result in creation of safety stock. If demand is strong during lead time, it will result in out of stock situation and might result in loss of customers. This result in uncertainty in estimation of reorder point. Above cases clearly shows that in P system, estimation of reorder point is dependent on variation in demand both before and during lead time. Resolution of this uncertainty requires understanding the concept of service level. Estimation of reorder point, how much to order. As seen in above discussed sections, inventory position in Q system is affected by variation in demand both before and during lead time. So, batch size to be ordered should have protection level for both time periods. In case of P system, protection level was determined only for the demand variation during lead time. Suppose time period before lead time is denoted as P, after which periodic review of stock is done and during lead time is denoted as L, then total time per ordering cycle would be P plus L. So, quantity that has to be ordered to maintain a specific inventory level would be made for this time period. This is done in similar fashion as was in case of queue system. Demand variation data would be collected for both time periods rather than only for during lead time period. The quantity to be ordered for desired inventory level to be maintained would be sum of average variation in demand during time period P plus L and safety stock to buffer against variation in demand during same time interval. Thus, desired inventory level equal to average demand during P plus L plus safety stock during P plus L. D into P plus L plus Z into standard deviation into square root of P plus L, where D is average demand. P is time period after which stock would be reviewed. L is lead time. Z is number of standard deviations calculated from desired service level. Standard deviation is the deviation in demand D. Example: it is given that average daily demand of a product is 6 units with a standard deviation of 1.2 units. The variation shows normal distribution and stock is reviewed after every 60 days. Lead time is 5 days and company intends to maintain a service level of 95%. Estimate number of units to be ordered per batch. Solution: D equal to 6 units, standard deviation equal to 1.2 units, P equal to 60 days, L equal to 5 days at 95% service level, Z equal to 1.65. Putting these values in the formula, desired inventory level 6 into 60 plus 5 plus 1.65 into 1.2 into square root of 60 plus 5 equal to 390 plus 16 equal to 406 units. Comparison between P and Q system of inventory control. The application of one type of inventory control systems depends on number of factors such as type of demand, type of product, etc. Selection of a particular system depending on advantages and disadvantages is difficult as one's advantages are disadvantages of others and vice versa. However, because of increasing usage of technology in inventory control, Q system has more application than P system. Technology automatically indicates number of units left in the stock and how much is withdrawn in case of every withdrawal process as desired in continuous review system. Following is the comparison of two systems without getting into advantages and disadvantages. Comparison between P and Q system. How much to order? Continuous review system Q is the same for every order as stock is checked after every withdrawal. Periodic review system Q is different depending upon variation in demand. Time between order. Continuous review system is different for every order depending on variation in demand. Periodic review system is same for every order as order is placed and received after a certain time period. Record keeping is difficult as records have to be maintained for every withdrawal of items. Periodic review system is easy as records are maintained only once per cycle. Continuous review system type of items highly prized, critical and important items. Periodic review system items of regular usage used frequently and relatively lowly priced. P model special case. EOQ model and some of its variations were dependent upon the assumption of a constant demand rate. When this assumption is relaxed, that is, when the amounts that need to be withdrawn from inventory are allowed to vary from period to period, the EOQ formula no longer ensures a minimum cost solution. Consider the following periodic review model. Planning is to be done for the next n periods regarding how much, if any, to produce or order to replenish inventory at the beginning of each of the periods. The order to replenish inventory can involve either purchasing the units or producing them, but the latter case is far more common with application of this model. So, we mainly will use the terminology of producing the units. The demand for the respective periods are known but not the same in every period and are denoted by Ri demand in period I for I 1, 2 and up to n. These demands must be met on time. There is no stock on hand initially, but there is still time for a delivery at the beginning of period 1. The costs included in the model are similar to those of the EOQ model. K equal to setup cost for producing or purchasing any units to replenish inventory at beginning of period. C equal to unit cost for producing or purchasing each unit. H equal to holding cost for each unit left in inventory at end of period. Note that this holding cost H is assessed only on inventory left at the end of a period. There also are holding costs for units that are in inventory for a portion of the period before being withdrawn to satisfy demand. However, these are fixed costs that are independent of the inventory policy and so are not relevant to the analysis. Only the variable costs that are affected by which inventory policy is chosen, such as the extra holding costs that are. Example: an airplane manufacturer specialized in producing small airplanes. It has just received an order from a major corporation for 10 customized executive jet airplanes for the use of corporation's upper management. The order calls for 3 of the airplanes to be delivered and paid for during the upcoming winter months, period 1. 2 more to be delivered during the spring, period 2. 3 more during the summer, period 3, and final 2 during the fall, period 4. Setting up the production facilities to meet corporations' specification for these airplanes require a setup cost of $2 million. The manufacturer has the capacity to produce all 10 airplanes within a couple of months. When the winter season will be underway, however, this would necessitate holding 7 of the airplanes in inventory at a cost of $2 lakh per airplane per period until their scheduled delivery times. To reduce or eliminate these substantial holding costs, it may be worthwhile to produce a smaller number of these airplanes now and then to repeat the setup, again incurring the cost of $2 million in some or all the subsequent periods to produce additional small numbers. Management would like to determine the least costly production schedule for filling this order. Thus, using the notation of the model, the demands for the particular airplane during the 4 upcoming periods are R1 equal to 3, R2 equal to 2, R3 equal to 3, R4 equal to 2. Using units of millions of dollars, the relevant costs are K equal to 2, H equal to zero point 0.2. The problem is to determine how many airplanes to produce, if any, during the beginning of each of the 4 periods in order to minimize the total variable cost. The high setup cost K gives the strong incentive not to produce airplanes every period and preferably just once. However, the significant holding cost H makes it undesirable to carry a large inventory by producing the entire demand for all 4 periods at the beginning. Perhaps the best approach would be an intermediate strategy where airplanes are produced more than once but less than 4 times. So students, let us now summarize that we have learnt in this module. Periodic review system P of inventory control is used where orders are placed after every fixed and regular time interval, resulting in certainty in order making. But such systems get affected adversely by fluctuation in demand both during and before lead time. Also, as orders are made after specific interval, thus time between orders for each cycle remains same, whereas because of variation in demand, quantity order could be different. For instance, if demand is high before lead time, making consumption of inventory quicker, so manager tends to order for higher quantity. Whereas if demand is slow, then manager tends to place a lower order to maintain desired inventory level. Thank you.